Welcome back. This is week 7 of our graduate statistics. We're continuing to explore the idea of sampling variability with the goal of trying to estimate what we can expect in terms of variation in our uh, statistical estimate of interest, here the mean height, without having to sample multiple times. So we just played with the app. And the desirable thing, the thing that we're after here, is to use estimates of population parameters obtained from one sample and then define sampling distribution, right? So we don't want to have to sample 1,000 times to construct a sampling distribution that then we can get the mean and how much the mean is expected to vary from sample to sample to sample, right? We want to get estimates of the population from one single sample. One sample. I want to be able to get from one sample to the sampling distribution so that I can say things about my population of interest that I don't know about, right? And that's what the central limit theorem is all about. You probably heard it a bunch of times, and people don't take the time sometimes to explain why we use it. Why is central limit theorem important in statistics? And that's why it's important, because it helps us get from the data that we have in a sample to the sampling distribution without having to go through the labor of sampling a gazillion million times, right? So the central limit theorem says that the distribution of sample statistics, regardless of whether or not your distribution is normal, the distribution of the data is normal in the population, the distribution of the sample statistic, like if you sample multiple times and get the means multiple times and plot the distribution of the means, or plot the distribution of percentage differences, or plot the distribution of standard deviation, that will be nearly normal every time. And there are some criteria to be able to use the theorem, but if the criteria hold, then the distribution of the sample statistic will be nearly normal, centered at the population mean, and with standard deviation equal to the population standard deviation divided by the square root of sample size, because we know it's smaller than the standard deviation of the population, but we can adjust by dividing by the square root of sample size. So here is the representation. The distribution of a sample statistic, for example, the sample mean, is going to be normal. That's the shape. The center will be the mean of the population, the thing that I want to know about. And the variation expected in the means, if I were to sample over and over again, is the variance, the standard deviation of the population, divided by the square root of n. Because the bigger the sample size, the smaller the estimation will be, right? The smaller error in estimation I'll have. And of course, I never know what the mean of the population is. So I will try to estimate that from my one sample by computing the mean of my sample. That's a pretty good estimate of the mean of the population. Of course, it will be better the bigger the sample size, but this I will know by computing the standard error. Again, I do not know the standard deviation of the population, but I know the spread of my sample. So I know the standard deviation of my sample, and I know the size of my sample. So I can compute, basically, I know that the sampling distribution will be normal. I know that we'll have the mean of the population, which I will estimate from the mean of my one sample. And I know it will have a spread that relates to the size of the sample I took. So of course, my precision will be more or less depending on the size of the sample, but I can compute that spread using the standard deviation of my one sample. So I don't have to do the crazy multiple sampling, which would be expensive and pretty much make every single researching possible. So I mentioned that the central limit theorem will not apply all the time, but it will apply when particular things hold true. One thing that needs to hold true is what we call independence. Sample observations must be independent of each other. So if we're trying to figure out what's the height of women in the United States. I cannot sample everybody from the basketball teams in the United States because that will be biased, and then central limit theorem will not work, right? So the individuals that I'm sampling are not independent from each other. Their heights will be related by the fact that they're all basketball players, right? So you have to have random sampling such that the height of one individual has nothing to do with the height of the other. I cannot sample only from going to a family and sample everybody there, going to another family and sample everybody there, because then the height of one individual will be related to the height of the other through genetics, right? So the first thing is independence. And if you're sampling without replacement, which is typically the case when I'm doing a survey or if I'm measuring the heights of females, I would not sample randomly a person, put the person back into the pack to run the risk of sampling that person again, right? So I'm sampling just one time each individual. If they're in the sample, I counted their data, I'm not seeing them again. So that's sampling without replacement. The sample should not be larger than 10% of the population of interest. And now you're saying, so you said the bigger, the better. I said the bigger, you're going to get closer to getting in one sample the true estimate. But then the central limit theorem might not apply if you start getting too many people, because then the independence criteria starts getting violated, right? So you can't guarantee for sure independence, but you can increase the chance of independent measurements if you're not taking so many people that then those dependencies start occurring, right? So if you're sampling almost everybody, it will be impossible not to have people from the same family in the sample, for instance, right? So you want samples that are not greater than 10% of the population. Those are ways of maximizing your chance of having an independent sample. So 2, the other criteria is sample size. It has to do with sample size and skew. The population distribution is normal, should be normal, or if skewed, the sample size is large. Rule of thumb, greater than 30. That means that if the sample size, if the particular data is not distributed normally in the population, that's not a problem. You can the sampling distribution will still be normal if you have a large enough sample size. And the rule of thumb is that it should be greater than 30. So if you go to back to the app, I'll try to show you how this plays out. Go there and I'll meet you in a bit. So here's what I was telling you, that here's a sampling distribution that we can compute. And up to this point, we were sampling from a normal distribution. If we're sampling from a normal distribution, the sampling distribution will look normal, right? It will have the mean that's close to the mean of the population, and we'll have the spread, which is the standard deviation of the population divided by square root of n. That's the relationship that was discovered through those simulations. Now imagine I'm going to sample from a very, let's say, medium skew. Here's the population distribution. Very, very skewed. And we're saying that the sampling distribution will still be normal if I take sample sizes that are large enough. If I take sample sizes that are very, very small, say 10 individuals, 9 individuals, you can see how the sampling distribution gets skewed, just like the population distribution. But if I increase sample size, typically around 30, you start getting the sampling distribution to be normal. And that's where the 30 comes from as the magical number for sample size that we call from 30 and greater a large sample size. It's because you get a sampling distribution that is normal even though your data might not be. That's where the magical number comes from. It comes from the fact that through simulations, you can see that the sampling distribution approaches normal at around that sample size for skewness that are, medium up to medium size. If you're very, very skewed, you may still not be quite there with 30. You might need slightly larger sample sizes. And if you have only, very low skew, you don't even need that large a sample size to still get a sampling distribution that's pretty normal, right? So those are the criteria in terms of distribution and sample size. Either you have a normal distribution and then sample size won't matter that much, or if you do have a skewed distribution, a highly skewed or mediumly skewed, then you want larger sample sizes, magical number larger than 30 for a central limit theorem to apply and allow you to compute margin of errors, confidence intervals, so on and so forth, which we'll see next. Okay? Just one more demo. What if your distribution is uniform, like this? Do you still get a sampling distribution that is normally distributed? And the answer is yes. Even if you have a completely uniform distribution, you will still get, if you sample multiple times from that uniform distribution, you will get the means every time. And then if you do the distribution of the means, they will look pretty close to normal. If you have a sample size that's large enough, it will approach normal more and more, so as you increase the sample size. Okay? All right, so back to our class. So one more time with filling. We're trying to get data from one sample and construct the sampling distribution with the idea that we want to get not only an estimate of the mean of the population on a variable of interest. Here, our goal is to figure out what's the average height of women in the United States. You know, if I get a sample and I just look at the average, sure, I'll get an estimate of what the population looks like, but it would be nice to know what the margin of error is in my estimate. And for that, I need the sampling distribution to tell me how much variation I can expect in my estimate given my sample size. And we can construct that using the central limit theorem, because the distribution of a sample statistic will be normal with a center that's close to the center to the mean of the population, and we can estimate that with the mean of our sample. And the spread that will characterize our margin of error, that's part of the process of getting to the margin of error, equals to the standard deviation of the population divided by the square root of the sample size. And that standard deviation I can estimate, which I don't know, right? So I can estimate from my sample standard deviation. And central limit theorem will hold when we have independence of our observations, and we cannot guarantee that, but if we have random sampling and if the sample is less than 10% of the size of the population, we're at least safe-ish that that's the case. And also, if the population distribution is normal, it holds, or if skewed, the sample size needs to be large, and the rule of thumb is larger than 30. If these conditions hold, we can use the central limit theorem to construct our sampling distribution and get our margin of error from data that we obtain from just one sample, which is what we said the challenge was. So again, I explained to you why we want sample sizes that are less than 10%, because the larger the sample, the harder it is to guarantee independence. And we also went to the app to understand where the 30 comes from, right? If I'm sampling from a non-normal distribution, a highly skewed distribution, or a uniform distribution, the sampling distribution will still be normal if I have a sample size that is 30 or more, rule of thumb. So again, if I sample from a highly skewed distribution multiple times, my sample distribution will not be normal, but my sampling distribution might still be normal if I get a sample size that's large enough. If I see a sample size of 20, look at the sampling distribution, it's kind of skewed. If I get sample sizes that are larger, now I begin to get a sampling distribution that is normal looking, even though my sample distributions are skewed. Okay? So we'll come back, we'll apply the central limit theorem and distinguish better in our heads what's the difference between the sample distribution and the sampling distribution. All right, see you soon.